we're now going to have a look at optical isomerism, and this comes under stereoisomerism, which we have looked at before. And if you remember the definition of stereoisomerism, it's where you've got compounds with the same structural formula, but different arrangement of atoms in space. And the examples we've looked at before, the types we've looked at before are EZ isomerism, which are present in alkenes, and we've also looked at cis-trans isomerism, which again we've looked at it in the context of alkenes. And now the type we're going to look at is optical isomerism, which is going to be applied to some organic molecules that we've already looked at. Right, so let's look a little bit closer as to what we mean by optical isomers or optical isomerism. So I'm just going to write out the definition and then discuss it with you. Okay, so optical isomers, as we said, it's a type of stereoisomerism, so they are stereoisomers, so they can have the same structural formula, but they are non-superimposable mirror images of each other. Okay, so this is the part that I just want to focus on for a second. And the example I'm going to use, I don't have any chemicals at hand, but the example I'm going to use are my hands, okay, because hands are an example of optical isomers. Now, as you know, your left and your right hand are mirror images of each other. Okay, as you can see, there'd be a mirror line down the middle, and they are mirror images of each other. Now, what we mean by non-superimposable is that we cannot impose one over the other and make it exactly the same, okay? They are mirror images of each other, but I can't impose one over the other. As you can see, they're not going to be exactly the same. Okay, so that's what I mean by non-superimposable, okay, but they are mirror images of each other. So my hands are examples of optical isomers. Another word for optical isomer is enantiomers, which you might come across in textbooks or on the internet, so it's worth knowing that as well. So you can say that your hands are optical isomers of each other, or they are enantiomers of each other, okay, both would be fine. Right, now in the context of chemistry, let's have a look at it in a molecule that we've looked at recently, and they are alpha amino acids. Okay, so we've looked at alpha amino acids where you have both your carboxylic group and your amine group attached to the same carbon. Okay, so both the carboxylic acid and the amine group are attached to the same carbon. The R represents any kind of carbon chain that we have for the amino acids. Okay, now these alpha amino acids are classed as, or they can have optical isomers of each other, or they can show optical isomerism because they have a carbon that is bonded to 4 different groups. Okay, as long as that R group is none of these 3, this would apply here as well. Okay, so where a carbon is bonded to 4 different groups, and we call that a chiral carbon, or you can call it a chiral center, both would be fine. Okay, so a chiral carbon is a carbon that is bonded to 4 different groups, and that's very, very important because that's going to help you identify these chiral centers, these chiral carbons, and therefore show and draw the optical isomers of that compound. Okay, so as long as that R group is not one of those 3, so I'm just going to do an example. I'm going to say that R group is just a methyl group. Okay, so this alpha amino acid is going to have an optical isomer. Okay, and we're going to look at how we draw that and how you should draw it in an exam. Okay, these have to be drawn in 3D. That's very, very important. So you draw your chiral carbon first. So that's the carbon that's drawn with that's attached to 4 different groups. Given that we're drawing it in 3D, that chiral carbon has a tetrahedral shape around it. So I always start off by drawing out the skeleton of it. So you have 2 bonds that are in the line of the board. You have 1 bond that is a wedge bond that is coming out of the board towards you, and you have 1 dashed line that is going into the board away from you. Okay, and then you just put your groups in. It doesn't actually matter at this stage which order you put everything in. Okay, so that molecule that I had on the board earlier, I've just drawn it in 3D on this side. Right, what you now need to be able to do is draw the optical isomer of this. Okay, so what you need to do is draw a mirror line down the middle like that, and then essentially you're just going to draw the mirror image by seeing where everything is on this side of the board. So always start off by drawing the chiral carbon in the middle. I then draw my skeleton back in, but remember you're drawing the mirror image. So you have the 2 that are in the line of the board going away. You have your wedge line going in, and that one there. Okay, and then all you do is you draw the groups in as they are as the mirror image. So you've got your hydrogen here. Over here you've got your NH2. Over here you've got your carboxylic acid. Now see how I'm drawing my carboxylic acid over here. Okay, in terms of connectivity, the bond should always be to the carbon, and therefore I've just flipped it there. Same way the bond for amine should always be to the nitrogen. And then you've simply just got your methyl at the top there. Okay, so now I have drawn the optical isomers of this alpha amino acid. Okay, and this is how you should draw it in an exam. You draw 1 optical isomer in 3D, you draw the mirror line, and then you draw the mirror image of that one there. Okay, now at the moment it might not really make sense in terms of them being non-superimposable images of each other. So I do have some molecules here, some molemods here that I've got. So essentially I've just got a tetrahedral carbon, so a carbon bonded to 4 different groups like that. I'll pop that down there, and then I have essentially just got the mirror image of that compound here. Okay, so imagine if I'd done this in 3D, mirror line down the middle, carbon in the middle, green groups here, purple, orange, and then the blue at the top. Okay, so as you can see, they are mirror images of each other, mirror line nicely down the middle there. Okay, now what I'm going to do is I'm going to try and impose one over the other, and as you can see, it doesn't work. Okay, so if I line everything up, I'm trying to impose one over the other just by popping it on top. The purples line up, the blues line up, but as you can see, the greens and the orange don't line up. Okay, so these are mirror images to each other, but we cannot impose one over the other, and therefore they are optical isomers of each other. Okay. And that's why this chiral carbon thing works. If you find a carbon that's bonded to 4 different groups, that will give rise to optical isomerism. Right, let's have a look at it in the context of an exam question. So what you're kind of likely to get in an exam, what you should do to help you answer it. So I'm just going to draw out a compound, a organic compound, and what we're going to do is we're going to identify any chiral centers in it. Like so. Okay, right, now so imagine this is in an exam setting, you've got this question and it's asking you to identify how many chiral centers are there. Okay, so what you need to do, if you have identified a chiral center, the way that you should show it in an exam, and you'll see it being done in textbooks like this. So for example, if I've got a chiral center here, so that carbon is the chiral center, all I do is a star next to it. Okay, and that's what I'm going to do in this compound over here. I'm just going to draw a star next to that chiral center, and that's what you should do in an exam as well. Okay, right, so let's just start off at this end, and we'll start off with that carbon. Now what you need to know is any carbon that is part of a double bond will not show will not be a chiral center. Okay, the reason being is because it's then attached to 3 different groups. It's not attached to 4, and therefore it cannot show. It cannot be a chiral center. Okay, so this one here cannot be a chiral center because it's in a double bond. This one here cannot be a chiral center because it's in a double bond. Okay, if we move to this carbon over here, one side is bonded to all this stuff over here, other side is bonded to this stuff over here, other side is bonded to this stuff over here, and which has not been drawn in, but it's also bonded to a hydrogen. Okay, so this carbon here is bonded to 4 different groups, and therefore this here is a chiral center. Okay, moving around the ring, I'm going to go in this direction. Again, this carbon's in a double bond, so therefore cannot be a chiral center. This one is in a double bond, so it cannot be a chiral center. This one over here, hopefully you can see, is bonded to this group over here, which is different to this group over here, which is different to this group over here, and it's also bonded to a hydrogen, which is obviously different, and therefore this carbon here is a chiral center. I'm going to keep going around the ring. This one over here, again, bonded to 4 different groups. So this group here is different to this group here, which is different to this group here, and is different to the hydrogen. So this too is a chiral center. This carbon here is part of a double bond, so therefore cannot be a chiral center. Oxygen obviously cannot be a chiral carbon. Let's move down to this branch over here. Okay, now this carbon here is bonded to a methyl group, and it's bonded to a methyl group, and then therefore bonded to that and a hydrogen as well. And given it's bonded to 2 methyl groups, because they're not different, this carbon here cannot be a chiral center. Okay, so given that it's bonded to 2 methyl groups, it cannot be chiral. This carbon over here bonded to 3 hydrogens. This carbon over here bonded to 3 hydrogens, therefore cannot be chiral. Moving down this branch over here, this carbon is bonded to an amine group, bonded to a methyl, bonded to this whole ring over here, and bonded to a hydrogen, and therefore they are 4 different groups, and therefore this is a chiral center. Okay, this carbon here bonded to 3 hydrogens, therefore cannot be chiral. Nitrogen here cannot be chiral. Okay, so in this compound here, we've successfully identified 4 chiral carbons, and we have shown those chiral carbons by drawing in those stars. So that's what you should do in an exam if you are asked to identify the number of chiral carbons, or actually draw in those chiral carbons in an exam.